Alright, so AC power complex notation example 2, right? So we are going to look at the problem, go through it and see what we need before we start. So let's go to the problem. It's saying that we have a small installation, just installation. Small installation consists of the following loads, right? Connected in parallel to a single volt. We'll talk about this single phase voltage, this single phase source supply. But let's deal with this question first. Having a 240 volt and then 50 hertz, right? This is RMS, right? So you're seeing that the power source is connected in parallel to all these. So like to make things simple, let's see if we can simplify it. So if there's a parallel voltage source, right? Let's see. Let's just use one because straightforward. So that's a 240 volt, right? And that's 50 hertz, right? So this is the supply, right? 50 hertz. Oh. Right, and this is connected in parallel. It's connected across, right? Okay. It's connected across. All these parallel loads are connected across the voltage source, which is this that we've drawn. So let's see if we do it this way. This will mean that this will be the first one. If this is the motor, let's make a symbol for the motor, something like this. Okay, so that's the motor. Right. The next one is the what? The radiator. Let's keep it this way, something like this, like a car radiator. Right. And then the next one, what do we have? The next one is what do you call it? Fluorescent lamps, right? So let's see. Let's just make it sort of a resistor, right? Let's see. Let's make it a bulb. So let's see. Okay, let's make it this way, right? So this is all the circuit simplify, right? So what they're saying is that let's see. The first one is saying we have a motor, fan motor, right? Taking an input. So let's pay attention to this one here, right here. We are seeing VA. So this will mean now this is what apparent power. This power factor, right? And it's lagging, right? Okay. And this is this. They are saying the B, the radiator, this just watt, right? So this is what power. Okay. Operating at a unity power factor. This will mean that we have, because we've seen that what's the name? Power is equal to apparent power and then power factor times power factor, right? So if they are saying that the power factor is 1, so that will mean that P is equal to S, right? This for B. We're talking about what's here, right? Okay. And then the number of fluorescent lamps taking, right? So that's that's the input, right? So this here is the input, and there's still VA, so that's just power. This power factor still lagging, right? Okay. So let's look at it very well, so we don't confuse ourselves. The question says find the total current, right? So someone will be saying that if we are trying to find the total current, if our aim is to find the total current, why don't we just add this apparent power here, add this one will still be apparent power, have the same value as the apparent power, add this one, and then add this one, and then we use what's the name? S is equal to I V, right? And then we just see I is equal to S on V, right? Why wouldn't it work? It won't work because all these ones, so look at this, this input, right? This is what, okay, it's the same as S will be the input, right? And this one here is what, taking, right? So this will mean input as well, input, right? But the question says what, off the load, right? So the total current, the total power, the total apparent power, and the power factor of the load. So all these things are of the load, and this of the load will mean that output, right? So you can't just use that one. So that's what we do. This will mean that before we are able to find, we'll be able to find all that we are looking for, we have to look for everything that's output, 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 right? So let's see. So if we take a particular one, so here's where we can use some sort of table to actually see what's happening, right? So let's see. If we take them one by one, so let's see if we take the motor, right? How should we name them? Okay. We'll just use ABC, right? So we have the loads, right? We have the loads to be, let's see. Okay. So we have the loads, we have A, we have B, and then we have C, right? How they've been given. These are the loads, and then we have their okay. These are the loads. It's always important that you look at the question and you look what they are trying to ask you to find. You understand the question very well, and then look for what you need to find those, right? So let's see. So these are the loads, right? And then they've been given their input already. That's their apparent power, right? Which is the S, right? So we write that somewhere. Let's just write S input, right? Yeah, S input. Okay. And you get to see why we can't use the power apparent power given to us directly, right? This is input. So let's see. So the first one, that's A. It says that the input apparent power is 1.5, is in K, right? So let's write the unit to make everything is in K VA, and that's what 1.5, right? So everything here is in kVA. Let's to make it clear so we see what's happening. Okay. Okay. So here we have K. Let's use something else. K V A, right? So 1.5 for A. B, what do we have? We have this. It says that the what do you call it? The power factor is 1, so that will mean that P is equal to S. So we can still write 1. It's 1000, so that's 1. So we can just write 1.0 here, right? 1.0. And then for C, what do we have? Where's C? Okay, C, the input power, apparent power is given as this. Because of the VA, we know it's apparent power, so that's 1.2. Okay, that's 1.2, right? So before we can find the current, that will mean that we have to find the total input power, right? Because the current that we are asked to find is the current output, right? But we can't use current input to do that, right? Because we don't know the total power factor. So what we do is that we have to use the power, we have to find the power output, right? Okay. And to do that, we need a S output, right? And we need what? V output, right? Let's see. Okay. And because we don't know the V output for this particular one, and then looking at the circuit very here, because they are all in parallel, if we consider this whole thing as 1, because it's they are in parallel, meaning that the voltage across them will be what? There won't be a, because the voltage across them is the same as that from the supply. Clearly we can see that V out, right, is equal to, write this one. Consider that this V out here is the same as the V in, right? So meaning that here we can use the V in here, right? Yeah. So the only thing left will be for us to find the what do you call it, the S out, right? How do we do that? We know that S, right, is composed of we have the power, right, and then we have the apparent power, right? And then from each and every one of this, because we have power factors, we can find that, right? So let's see. So now that will mean that we have to find these of each and every one of these components and add them together, right? In order for us to get our S, which is our apparent power. So let's go about it, right? And then each and every one of them have their own power factor already, right? So let's see. Now for us to do that, we have the S, so that will mean that we need the power factors. We have the power factors already, which you know that to be cos S, okay, cos the phase angle, right? For the A, we have that to be, let's see, 0.75, right? In fact, we have those values already, don't have to even point them again. So straightforward, what we'll do is that now to find our S, we need P and Q. So we need P and Q. The first thing we do is that we'll try and find the P, which is the power, right? So power, right? And we know the power is the S, right? And then the power factor, right? Okay. So now we'll go about that. So let's see. We start with the punching of values. It's very important that before you start the question, you know what you are trying to find from the problem, right? And then you know what you need in order to find what you want to find or what you need to find, right? So that's what we did when we started. And we've seen everything that we need to find. We've seen the values. You understand what we need to do now. So now we're going straight for the problem. Now we're trying to find the power of each of them, the apparent power, and then we add everything up and get the power output, right? Apparent power output. Okay. So now P. So in order to find the P, we need the S, right? So let's see X. Let's see. To make our work easier, let's see how we can use the X, and then we'll do a power factor, right? So let's make the power factor B, right? Okay. Now for A, so now we're working on A, right? There's one way to use the calculator to help you. So for the A, we know the power factor is what? The power factor is what's A? 0.75, right? So when we solve 0.75 minutes. So we are using the power factor. We are using apparent power and the power factor. So let's see. Apparent power, let's make it A. So apparent power times power factor. Let's make it F. Okay. So now we know apparent power is what? 1.5. Power factor is 0.75. Okay. And that will give us a power of 1.125. Let's see. 1.125, and all this, as we've said, the unit to be kilo, right? And kilowatt here, right? Okay, go to the next one. What do we have? That's B, right? We have the apparent power of 1, and we have the power factor for the B1 to be 1. Right, so where's it? Unity power factor, yeah, unity power factor. So that's 1. What do we have? We have power of 1. So let's see, because we are doing DP 1.0. Go to the next one. This 1 point. Right. Okay. The next one, the apparent power is 1.2, and the power factor is, let's see, 0.95. 0.95. But then there's one thing that we must pay attention to, right? We've said this already, that if the power factor is lagging, right? If the power, where is it? We discussed it. We discussed this already. If the power factor is lagging, as we see here, that will mean that we'll talk about the apparent power. Now let's finish with the power and see. The power is all positive, as we've seen already. The power is always positive. Right, so we have 0.95. Let's see. Let's confirm we did something. Okay. So we said the apparent power, which is this, as we are seeing here, it's 1.2, and then the power factor is what? 0.95. Okay. And I'm getting 1.14, right? So 1.14, right? And we have all that for the, what's the name? The power. And now the next thing we have to do is that we have to find the, what's the name? The apparent power for each and every one of them. And how do we go about that? There's the thing. Because we have the power factor for each and every one of them, there's a way that we can find the other one, right? So let's see. We've been given we know power factor is cos theta, right? And now for us to find the Q, we know Q is equal to S, which is the apparent power, right? And then we have sine, and we have theta. But here's the case, we have cos theta. We don't know the sine. But then there's a relation we can use. It's very common. Where we have cos theta squared plus sine theta squared is equal to 1, right? And if we have the sine or the cos already, we can find the what do you call it? The sine theta. Right, so let's see. So that will mean that in order for us to find sine theta is equal to square root. So let's do it step by step. That's 1 minus cos theta squared, right, square root. So that gives us our sine theta and then we'll be able to find our Q, right? So let's find the sin theta for each and every one of them. Let's see. So the first one, the power factor was 0.75. So let's see. So that will mean that this is a relationship that we are using. We are using this one right here. So our x will be square root. We have 1 minus, right? Cos, let's say power factor. The power factor we said is f, right? So let's see, f. We're using f to represent it. F squared, right? So we punch it in the calculator, access the values, and then we get what we need. Straightforward, right? So for the first one, a, we are trying to work it for a. So now we let's see. Should we do it straightforward? Okay, let's do it straightforward. So now the formula we are using is that we are trying to find Q. We know Q is equal to S sine theta, right? So that's what we're trying to do. This formula here we see on the calculator is giving us our sine theta, right? You can go over it, you understand why. So we've seen us here. We are just putting the apparent power by the symbol that we use for that one is A, right? We're just going to put A there, and the calculator access the values, and then we put it there. That's another way to help you punch everything faster, right? So now this will give us our Q straightforward, right? Okay, so let's see what we get for the apparent power. And then here is where we look at things, right? We look at the power factor. So we know clearly that you said that if the power factor is what's the name, is lagging, that will mean that the apparent power is positive. If it is leading, then the apparent power will be negative. We've seen this already. Right, so here everything is lagging. Here it needs to always lead is unity, so that's it. And then here it's also lagging, right? So lag. So that will mean that we don't change the values of the Q that we have here, which is the reactive power, right? Reactive power. And we said that's what's the name? That's S sine. Let's zoom in and write this up. That's S sine theta, right? And has a come on, S sine theta, and has a unit of kilo V a volt amperes reactive, right? So we've written the unit. Okay, so now let's see. We start with the first one, right? So we know A, there's more A in the formula here, and the calculator is the apparent power, and the F is the power factor, right? I'm just using something that I can relate to it. Always do it that way to make your work easier. Okay, trying to find the Q. Right. So calc, the apparent power for the A is 1.5, right? And then the power factor for the A is 0.75, 0.75, right? Okay, and that gives us 0.99. Let's do 4 dp. 0.9921, right? We go to B. Okay. B, the apparent power is 1. The power factor was unity 1, and that gives us 1. Let's see, that gives us 1 here. Let's make it 1.0, right? Oh, it gives us 0, sorry. So let's see, apparent power is 1, power factor is 1, so that gives us 0. That gives us 0. You must be very familiar with the calculator that I use. Very familiar. Yeah. So now we go to C, right? For C, the apparent power is 1.2, right? The power factor was 0.95, yeah, 0.95, and that gives us apparent power of this, which is, let's do 40, 0.3747, right? The units are already there. So we have all these. That will mean that we will be able to find our current, right? And then we'll be able to find our S input, and we'll be able to find our current, right? So let's see. Try and find current first. So current output is equal to S in S output rather, all on V in. We say it's the same as the V out, right? So let's just write out. Okay. So now do we have everything we need? Yes. And we said that S is equal to square root of P squared plus Q squared, right? We can put that there. We know V already. So let's see. Here I'm just using formula straightforward. If you know it, just go straight for it, right? Okay. So that will mean we have square root here, and we have P squared. So we have something squared, and then we have something else 2 squared, right? And then here is where we have the voltage out. Okay, so let's see. So here we need P, meaning that if you are trying to find this thing for the whole show, right? It's saying of the load, meaning that we are considering all this, to be in some kind of like one box, right? Minute. Meaning we are considering everything here to be in one box as just one load, everything together, right? So that's what it's saying. So that will mean I will have to add up all the P's and all the Q's, right? Not for us to be able to, so we add up all the P's and all the Q's, not for us to get our S, right? So let's see. Then again, if you have the calculator by you and you know what you are doing, you can do it straightforward. You don't have to add up everything, right? But also you can do the total here just to make your work easier. Total, you add this ones here, you add this, you add this. That's also fine. But now here I'm just doing it straightforward, right? So I know that I need P and I need Q. For P, I have a 1.125 plus. So now I'm adding this side. I'm adding here. Okay, and then 1, right? And then 1.14, right? I'm done with that one. Okay, so now I'm adding this one, the Q's up. So let's see. Okay, and then I'll need let's see, 0.9921 plus this is 0. The next one is 0.3747, right? And the Q have been added up. The next one is for the formula. I found my S, right? P and Q. Now I need a V. The V is the power input. The V out and the V in are the same. The voltage input, right? The voltage in and voltage out are the same. That's 240, so 240, right? And that gives a current of this. But then remember, let's see. Remember that the unit for S is in what? Kilo volt amperes, all right? And this is just volts, right? So that means that there's some 10 to the power 3 there, right? So that means that we have this. So the unit is very important. 0.01. Let's do 4 dp. 47, right? Kilo. Let me make it different. Kilo. And then we have, because it's current, we have what? Amperes. So if I multiply all this by 10 to the power 3, by 10 to the power 3, which is the kilo, right? And that will give me 14.7481, 40p. I choose to do it that way. Amperes, right? So that's what I get for the current. Always, it's very important that you go step by step. You know what you are doing, and then you go by that, right? So let's see. So now we have the current. So let's see. And of course, if you understand, you can go straight for it. So now we have the current. The next thing for us to find this is kW, right? So that's power. Meaning you have to add them up. We found that already. That will mean that we'll need let's see. We're adding up these guys. How we are solving it, we are just going by what has been asked in order. You can go every which way. The one you feel you can use to get to the answer you need. So at the moment we are done with this. We are done with the total current. Now we need the total kW off the load, right? The output, which is the power. So we have to add all these, right? So let's see. That will be 1.125, and then so we're adding these ones, right? Plus 1.01 plus 1.14, right? And that gives us a power So this is total power. Total power is 3.265, and that's a kilo. All right, so kilo watts. So, yeah. And so the next thing for us to find will be the apparent power, right? But then the apparent power of the load, and we know if you are finding that, that will be the output, right? But then looking at the table here, all that we have here is input, right? So we can't find that directly, but we know this is output, this is output, right? So now for us to find the S output, we can use this relation where we know the S output is square root, and then we have the power squared, and then we have the reactive power squared, right? So we can use this. That's what we are using. We have to find the total power. We've seen the total power to be this. We have that already. So that will be 3 point. The total output power. So that will mean the power of the load, right? 3.265. And we have the, what's the name? Total reactive power. We don't have that directly. So let's see. We can add them up. We have 0.9921 plus 0, and then plus 0.37, right? 47, and that gives us our total apparent power, right? Which is the output apparent power, or the apparent power of the load, right? So let's see. So that gives us the S of 40p, 3.5395, and because it's apparent power, we have a unit of what? Kilovolts amperes, right? So that's what we have. So now we've dealt with that. Apparent power done, right? The next thing is for us to find the power factor. And one of the commonest relations that come to mind is that when we're trying to find power factor, you know, we have what's the name? We have P is equal active power is equal to apparent power, right, times the power factor, right? So meaning that the power factor we are looking for, which is the cos theta, will be equal to power all over apparent power, right? And we have the values of this ones already. It's saying off the load, right? So we have the P total, right? P total out, and you have the S total out, right? These are the values that you use. If you use something different, it could be something else, because they are saying off the load, so they are saying output, right? So that's what they are looking for. And then we have the, so let's see, this will be this on that, and then we have the total power output to be 3.265. Oh, okay, 3.265, and you have the total apparent power to be 3.5395, right? So that gives us a power factor of let's see, 0.922 right? So here, how do we get to know whether it's leading or lagging, right? It will depend, and we'll look at that very soon. So let's see. So basically, this one right here is lagging, right? But you get to know that depending on the, let's see, the, what's the name, the value of the total Q that we have. We're looking at all that we have here, the total Q that we have, the total reactive power, right? If you add everything up, it ends up being positive, and we've seen this already, right? So we have something like this. We have let's see, real power here, and then you have reactive power positive, so positive Q. You have negative Q here, right? And we've seen that if the power is lagging, meaning the current is lagging, right? So you have a Q of positive, which will be about here, right? But if what do you call it, the power is leading, right, or the current is leading, that will mean that you have a Q of negative, a total Q of negative. So that will be power factor of the power factor leading, right? But here's the case that we ended up getting a Q that's positive, right? So that will mean that still the power factor, or the total power factor of the load is lagging, right? So that's what we have here. That's why we have the power factor of the load, or the output, lagging. Well, let's just make it lag. So lag, right? When it comes to the apparent power, sorry, the reactive power, right? You must pay attention to the whether leading or lagging, right? So that because it's the one that can be positive or negative, right? So now we have the power factor as well, right? So let's see, is there anything we're supposed to find? No, we are done with everything. So we found the, what do you call it, the power factor as well. when we started, this is just straightforward. When we started, we said that we can't add up these power straightforward here, right? Because why, there's the input, right? But they want us to find the apparent power, right? Or the total current. Everything is to be of the load, so that's output. So let's see. When we add these values up for the input, we get let's see. So that's 1.5 plus 1 plus what plus 1, and then we have plus 1.2, right? And that gives us 3.7. When you compare this one to the what's the name, to the apparent power or the total output apparent power, you see that this, what we have here is lower, right? Why? Because there is a loss, right? So this is the input. What we are seeing in the calculator here is the input. This one here is the input. But what we found here is the output. So it's clear that because it's a system, for every system there will definitely be losses, right? There will definitely be losses. The efficiency is not one, though it's not stated. That's why we see clearly that this is the apparent power, isn't it? Apparent power output, and then 3.7 kilovolt amperes is the apparent power input. So that's why we don't use that one directly. Yeah, so that's it. Right.